Now, in the last video, I assumed that we already have a configuration file how to fit the data. In this video, I will explain you how to do it, how to define one. For this, you select here a spectrum, then you select here Fit, Advanced. Well, at first it's telling you no peaks defined, which is true because we are starting over from scratch. Now, the first thing we need to do is to calibrate the energy range, the energy scale of this spectrum. Normally, if you always use the same instrument, you have this already somewhere, but here we start from scratch. So we go Tools, Calibrate. Here you have the spectrum and logarithmic scale, and up here you can make him search the peaks. And now you need to have some information already. Now, the easiest is that we used a rhodium X-ray tube. So this peak here, the coherent scatter to the right of the incoherent scatter must be the rhodium K alpha. It's down here, rhodium 45, and the line it's a KL3, which is the main part of the K alpha line. Then if you investigate historical paintings, you will normally have a doublet of these, which is the lead L alpha and the lead L beta. Now, and the lead L alpha has an energy of 10.55 kilo electron volts. Okay, so okay, and now you can switch to energy scale, and this should be all right. Now, the next step, looking at logarithmic scale, is to select the elements that are in the spectrum. For this, you need to configure, and you can select here now the peaks you want to fit. Go here and say, for example, calcium. Calcium is here. Fine. Potassium, probably there. Then we have this big peak. It's iron. And there's copper. And then we already saw there some lead. Now, if we now fit this, it looks terrible. It's not a good description of the spectrum. Now, this is for two reasons. Reason number one is we're using the entire spectrum and not just the good part of the spectrum. So this detector was not very sensitive to low energetic radiation, so there was a cut-off, and we should not include this in the fit. Also, we have here this near featureless parts above 17 kilo electron volts, so we also don't need it. The second thing is that we did not take the shape of the spectral background into account. So, first step is to find these channels, which are nicely shown here among other things, the upper right corner. So, this is 117. And this is 912. And always remember to check this, otherwise he's not doing it. Now, that's already a start. Problem is, of course, spectral background is not taken into account. There are two ways of doing this. We can either give him a function that he's fitting with the elemental profiles, like a linear polynomial of fifth degree. If we do this, we get something like this. Better, but not perfect. What we also can do is we can estimate the shape of the background. For this, we open here this window. It's a strip and snip configuration window. And it seems I'm not allowed to make it taller. Okay. Here you have now both strip and snip in the spectrum as an example. I normally set strip to 0 because it's a very slow algorithm, and I use snip. It just looks actually okay to us. Here you can say how wide you want to have the spectral window when using it. If you make it larger, you go further down. If you make it smaller, you actually go into the peaks. But 30 is a good value. Giving here the background smoothing some value, like 5 or so, is also a good idea if you have more noisy data. Very nice is also here the strip background use anchors. You can, for example, tell him that up here in this channel 340, let's say that, this is part of the background. Then he's treating it accordingly, and so you can take care of scatter peaks and so on. So this, of course, if you want to use it, you have to select here, include stripping. Good. Now we see here, this is the spectrum. We have here the spectrum in black, the fit in blue, and spectral background in red. It's nice, but it's not complete. Now we need to identify these remaining lines. And one way is, if you have it in energy mode, you can go to this area, select it, and you get a number of proposed elements that might be there. It is rightfully telling you this manganese here with its energy of 5.9. Good. Other elements that are there is, I can tell you, there's mercury from its L lines. There's nickel, we see it here. And then I think there's also some strontium. Yeah, maybe, who knows. Titanium, barium might be there. Then you have the lead M lines down here, and possibly some sulfur. And most of all, as we worked under air, we always have an argon signal in it. Maybe also some chlorine. Let's put it in there and see how it ends. Well, this is already a better description. But it's of course not perfect. What we see, for example, is here. This peak is a little bit too high. And there are actually two reasons for this. Reason one is an absorption effect inside the sample, which might be solved by selecting this. Well, it does not get really better. We see here that this shoulder of the peak is not correctly fitted. And this is because there's also some cobalt in the sample, as you can see here. So we undo this. And with the calcium here, we however have a real absorption effect because calcium is in the subsurface layer. Now we fit again. Better. The peaks here look a little bit bad also because we did not include the scattered primary radiations, rhodium L lines. Which is of course not perfect, but we will take care of that in a moment. So there are slight absorption effects here which create a problem, but not that dramatic. What we see here is that the lead gamma lines are a little bit too high compared to the L alpha and L beta. And for this there is a simple explanation. At the moment, PyMCA is assuming that we have a perfect detector. And if we go down to the attenuators, say him, so you can say here plot all elements are equally well detected. But it's a detector and we use the STD, so it's something like half a millimeter thick. Then suddenly you see the efficiency for high energy changes considerably. And now, not perfect here, but better. Also here, this improved a bit. And also what we need to take into account, there were something like 3 centimeters of air between the sample surface and the detector. Now this is getting better. And yeah, this is already a rather decent fit. There's some fine points that we will work out later. So if you want to improve it, you first have here the start, where you have here for the background estimation all the points. You have here the polynomial order. The fit function, it's basically a question, as long as you're in reasonable energy ranges of, I think, below 30 keV, the hypermet is okay, but for higher energies you need to get up here to the pseudo-void function to have a good fit. But it's basically, for historical paintings, not really a problem. Then there's a statistical weight. If you have this, the statistical weight is less on the intense peaks and more on the less intense ones. So now he's basically taking a lot of care of the peaks down here. If we switch this off, I'm not sure if we will see a difference in the spectrum. Yeah, we see here slight changes, but not significant ones. Yeah, down here, here's a change, because there's more statistical weight up here on the L-alpha line. Good. Then the number of iterations, the higher, the better the fit, but also the longer the measurement. Then the minimum chi-square difference is when he considers a fit finished. This button is if you use a fit strategy, which I do not use for historical paintings. And this is the most important line. Perform a linear fit fixing nonlinear parameters to initial values. This is necessary for speeding things up. To use it, you select Load from Fit. It gives you this nice explanation. And then you select it, and now fitting is faster. It's especially important if you do batch fitting of an entire data set. Then you, by this, get the necessary speed. Further, you have the detector, which is energy calibration, its noise, which is determining the energy resolution, the pile-up factor, if you try to handle pile-up peaks, and so on. You can give him here, for a more fundamental parameter-based approximation of peak ratios, the energy of your beam. If you have a synchrotron, it's very easy. Just need to give him 38.5 and a weight of 1. Or you can tell him, calculate with this tool X-ray tube. The peaks, we already had them. Up here you select the element, down here you select the lines, and he's showing them if you select them here in the spectrum. Peak shape. Peak shape is a little bit tricky. The point is, if you have a very strong peak, you're getting some tailing behind it. Especially if you, for example, investigate a massive copper object, you have a huge copper peak with a long tail after it, that if you do not take it into account will give you a lot of fake signals. You can use these approximations for treating that, but the problem, it makes the model a little bit unstable. Here you now can use a fundamental parameter approach to define your instrument. You have, for example, the thickness of air that's absorbing the fluorescence radiation. There's a dead layer of the detector, which is most of the time there. The detector window, additional absorbers, a contact layer, which is typical for Sealy detectors. You can define also here, you can add any material you like. You can have a Teflon contact layer. PyMCA does not judge, he just does what you say. If you do something wrong, it's your problem. Down here you can also define your own materials with its chemical composition. And which is very interesting is you can also directly write here a chemical formula like C1O2. Give it a random density. I honestly don't know it from mind how much it is. And he has it. He accepts it. It does change something in the low energy, but yeah. It is a very nice and elegant way. Now you can define not only a single material as a sample itself, you can also define a multi-layer. Then you select here multilayer, and in matrix you can determine the incoming angle and the outgoing angle of the radiation and define them here in multilayer. Okay. You can also do quantification either from the fundamental parameter approach with a fixed number of photons hitting the sample, and also from matrix composition relative to one of the elements. Problem, however, you need to really understand well your instrument, and you need to calibrate your model with reference materials, and it's not part of this tutorial, but it works rather well. And then there is also a part on Monte Carlo simulation. And so, here you go. Now, I have this, both the changes I made to it. It's not a perfect model. How to make it a perfect model we will discuss in the next video. Still, you can look at it as a peaks spectrum, and then you can ask him for a report. Select them here, folder, and you get an HTML file with an image, all the fit parameters, and a long table of elemental lines. You can also get the same table here. And of course, you can save and load the configuration in a file as you like. Okay, thank you for your attention.